You deploy a cluster of expensive, powerful GPUs, but the utilization stays suspiciously low. Latency flatlines, while power draw and memory bandwidth trigger infrastructure alarms. Historically, when performance lagged, the remedies were predictable. Better hardware, architectural tweaks, or aggressive batching were generally sufficient to squeeze out more performance. Large transformers have pushed inference across a qualitative threshold. Parameter counts have exploded, and context lengths have stretched by orders of magnitude, turning inference into an infrastructure-level challenge. When pushing higher batch sizes to improve throughput, systems now hit memory bandwidth limits long before exhausting their arithmetic capacity. This creates a new set of binding constraints. Memory movement and power budgets have replaced raw arithmetic throughput as the primary bottleneck for modern inference. The reason data movement dictates cost is found in the baseline energy costs of modern silicon. These ratios remain stable even as hardware generations evolve. This chart maps energy costs. INT8 math takes 0.3 picojoules, and FP16 takes 1.5. Moving data costs far more. Passing L1 caches to off-chip memory skyrockets the cost to 500 picojoules, creating a 1,700 times energy gap between compute and memory fetches. Because every inference step requires reading numbers from memory, the energy spent transporting data completely dwarfs the energy spent on the actual math. We can scale these microsilicon physics up to a 7 billion parameter model like Llama 2 to see the operational impact. At standard FP16 precision, the weights of a 7 billion parameter model occupy roughly 14 gigabytes of memory. During inference, the hardware must read every single one of those weights for every token generated. This transforms static storage into a massive, recurring data movement penalty. In addition to the weights, the system must read and write to the key value cache, which stores the attention keys and values for every preceding token to maintain context. For a 2,000 token context, reading the 14 gigabytes of weights and the 1 gigabyte KV cache results in 15 gigabytes of memory traffic per generated token. This data drag happens iteratively. The model is effectively brute forcing 15 gigabytes through the memory hierarchy for every word it outputs. Expanding context windows and the rise of reasoning models are compounding this traffic problem. This chart shows how memory traffic scales. At a 2,000 token context, we hit that 15 gigabyte baseline. The model weights remain a constant 14 gigabyte penalty, but the KV cache scales linearly. At 128,000 tokens, traffic reaches 78 gigabytes per token, 5 times the baseline. Reasoning models multiply this again, as they must generate far more invisible tokens to answer a single query. Hardware bandwidth and thermal limits cannot scale fast enough to meet this explosion in traffic. This is the efficiency wall. Translating that 15 gigabytes of traffic back into our energy metrics reveals that a single generated token requires roughly 1.9 joules. In a production environment serving 1,000 tokens per second, that results in a steady-state power draw of 1.9 kilowatts per replica. Strategies like dynamic batching or speculative decoding help amortize costs, but they don't reduce the underlying energy demand of each token. Architectural changes like mixture of experts or flash attention improve how data moves internally, yet the massive weight matrices still require fetching. Quantization addresses the dominant cost directly. By reducing the number of bits moved per token, it lowers memory bandwidth and energy consumption without requiring a model redesign. Reducing precision from 16-bit to 8-bit cuts the weight footprint in half, which linearly halves both the memory bandwidth constraint and the energy cost. Transitioning to the integer domain involves crossing a boundary between two distinct numerical worlds. Floating point numbers act like a zoom lens, using a mantissa and exponent to concentrate precision where values cluster. This flexibility allows for scientific precision across vast ranges, from astronomical distances to microscopic measurements, but the cost is high. Floating point operations require aligning exponents and normalizing results, which demands complex control logic and silicon area that goes largely unused during inference. Integer formats discard the exponent to create a rigid, uniform grid. Every number exists on a fixed spacing within a closed numerical world. This rigidity drives hardware efficiency. Because integer operations skip the overhead of exponent alignment, they require far less control logic and fewer cycles. Integer pipelines are shallower and denser, allowing more arithmetic units to fit on the same silicon area. This results in higher throughput and lower energy per token. If we strip away precision and force complex weights onto a rigid grid, why doesn't model accuracy collapse? Empirical data shows that models are remarkably resilient. Weight-only INT4 quantization of Llama 2 costs only 0.1 perplexity points on standard benchmarks. Trained neural networks do not rely on exact physical values. Instead, they encode relative directions, correlations, and influence. Because networks are inherently redundant and accustomed to noise from the training process, they can absorb the bounded approximation errors introduced by quantization. Pushing to extreme 3-bit levels causes quality to degrade more noticeably, requiring specialized mathematical methods to handle outlier weights. This leads to a central principle of model efficiency. The engineering objective is sufficient precision at minimum energy.